So this is the first unit that we have in our course for biology, and it is entitled Scientific Inquiry and Biological Organization. Frankly, although you can see the questions that are the big picture questions that need to be answered by the time this unit is over, it's kind of a catch-all category. It's kind of a catch-all portion of the course. The information isn't really packaged into something that relates to each other. For instance, we're going to deal first today with the scientific method. We will learn about the characteristics of life. We will talk about how to categorize that life, and just because it needs to go somewhere, this is also the unit where we will learn about and how to use a microscope. As I mentioned, we're going to start off with a topic that is one that I'm sure you've dealt with before. Probably starting in elementary school, you dealt with the idea of the scientific method, and hopefully as you've progressed through school, you've sort of added some layers of intricacy to your understanding of it. We're going to start off with the idea that science really is just a way that we try to explain how the world works. We can think of it in terms of chemistry, or we can think of it in terms of biology, or perhaps physics or earth science, but any science that you think about is just a quest to understand the world. And so in that quest, you're going to start off with a question or a problem of some kind, something that you want to know but don't. As we go through these steps and stages of the scientific method, I'm going to try to do so by using an example. So what question or problem do I have when it comes to my understanding of how the world works? Well, as a biology teacher, and in the state of Pennsylvania, where students have to take the Pennsylvania Keystone exam, my question or problem is, how can I get my students' test scores to be higher than they have been in the past? So we're going to use that as an example as we go through here. You can see that step number 2 is research. You want to find out what has already been done or what has already been figured out about your particular question or problem. It is extremely possible that when you do some background research, you may already find the answer. Somebody else has already had your same question or problem, and they have already figured out the answer or the solution to it, in which case, you're done. Step 2 is the last step. But what is more likely is that you won't find the exact answer to your specific question or problem, but you may find information that is at least related to your problem or question. So for me, let's say I do some research and I find out, okay, well, test taking, that's got to be about the brain, and I learn that the brain operates on huge quantities of sugar as its source of energy to fuel the body. We go on from there to step number 3, a step that I know you've all heard of before, which is the hypothesis. I know the standard definition for that you get from the middle school is it's an educated guess. I want to change that. It's not a bad description, but I want to change that to the word prediction. When you are stating a hypothesis within the scientific method, you are making a prediction about what you think the answer to your question or problem is going to be. And yes, it's an educated guess. It's a prediction based on some knowledge because, of course, you've just done research. So you ought to be educated on the general topic about which you are trying to explore. In my particular example, I want to know whether the idea of sugar can help my students' brains so that they will do better on a test. So I'm going to make a prediction. And you'll notice here in the screen it says 2 words, if and then. I'm going to put my prediction into the form of an if-then statement. So, if I give students a candy bar prior to taking a test, then their scores will increase. So I've set up a scenario with the if, and I've really made my prediction with the then. I didn't straddle the fence. I wasn't wishy-washy. I had to make a prediction. It's like if you were going to watch a football game and somebody said, well, who's going to win? You can't fumble it. You can't say, well, I don't know, it might be this team, it might be that team. No, you have to make a prediction. You have to pick a team. In this case, I said, if my students eat a candy bar, then their scores will improve. Maybe the scores will be the same as they would have been with or without the candy bar. Maybe they'll be worse. Who knows? But I've made the prediction that they will be better. From there, it is time to actually conduct an experiment. In that experiment, there are some essential things that must be incorporated. One of the ideas that must be incorporated is the idea of reproducibility. As it says here, the ability to perform the same experiment over and over again and to consistently obtain the same results. If I do this, if I give my students a candy bar and they do wonderfully well on the test, other teachers are going to want to know that. But if they perform the experiment and they get bad results, then I'm the one that looks stupid. You need to design a set of steps. Step 1, do this. Step 2, do that. And work your way through all the steps of the experiment in such a clear, concise way that somebody else could come in and follow your directions, do your experiment, and get pretty close to the same results that you got. This is one of those ideas that's easy to understand, but sometimes hard to accomplish. When we write a set of instructions, we know what we're trying to say, but sometimes others interpret those directions differently. So the idea of reproducibility is an absolute must, but not easily done. Now, what are some things that need to be incorporated in those experimental procedures that will be so reproducible? Well, you absolutely have to have 2 groups. You have to have a group that is your control group and a group that is your experimental group. In other words, you need a basis for comparison. You need to do something to one of those groups that you're not going to do to the other. For example, I'm going to have everybody in my experiment take a test. Let's say it's a test on biology. The control group will just come into my class one day and they will, after having been taught all the material and hopefully studied, they will take the test and I will grade it and that will be it. The experimental group will be doing all of those exact same things, except that I will also give them a candy bar. Once I can grade both groups' tests, I can then compare the scores. It's a basis for comparison. If I just brought everybody in and gave everybody a candy bar, how would I know if the candy bar helped or not unless I have something to compare it to? So you absolutely have to have a control group and an experimental group. You must also have a manipulated variable and a responding variable, or, as the vocabulary terms can be interchanged, an independent variable or a dependent variable. I've really already described those to you as I talked about the control group and the experimental group. A variable is something that, of course, varies. It differs. In this case, it differs between the control group and the experimental group. What was the one thing that I did differently to one versus the other? I gave one group a candy bar, and I withheld a candy bar from the other group. That is the manipulated or independent variable. I, as the experimenter, manipulated that situation. I gave one group candy, I did not give the other group the candy. As a result, what is it that is supposed to change? Well, hopefully test scores. And so that is the dependent or the responding variable. It depends on the independent variable, or it responds to the manipulated variable. Along the way, again, one of those things that's easy to understand but hard to actually achieve is that the person in charge of the experiment must have good controls, or you would say controlled variables. As it states on the screen, these would be all the variables that must stay consistent between the control and the experimental group. For instance, I wouldn't want to give my 2 different groups 2 different tests. I want to give them the same test. I want to give them the same amount of time to take the test. I would want them to both study the same amount. I would have wanted them to both experience the same lectures and labs and things like that that went into learning about the content of the test. You want to know whether the candy bar made the difference in the test scores. Therefore, everything else needs to be kept the same. Lastly, we need to incorporate the idea of a fair amount of data. You wouldn't want to base this on two people. One person gets a candy bar, one person does not. Whoever does better, that's who wins. No, you want 1,000 people, and 500 of them are in your control group, and 500 of them in the experimental group. The more data you have, the more valid your conclusions will be. Now, with all that data, you need to have it organized. That way you can make sense of it. If you put it into graphs, charts, tables, for instance, in my example, I would want to average the test scores of the control group and average the test scores of the experimental group and just compare those two numbers. And then when I can do that, I can draw a conclusion. Most important thing to note here is that the conclusion always refers back to the hypothesis. You made a prediction back near the beginning of the experiment. And so now it's time to say, okay, was that hypothesis correct or incorrect? And there's two ways to say that. You can either say the data supported the hypothesis. In other words, when I collected all my data, it confirmed that my hypothesis was correct. Or the data refuted the hypothesis. Hey, when I collected the data, it turns out I was wrong.